Good afternoon, everyone. Welcome to the last talk of the session. Uh, my name is Manas Paliwal, and I work as assistant professor uh, at Metallurgy Department in IIT Kharagpur. Uh, Today, in this talk, I be would be presenting some of the work that we are doing with respect to modeling of phase transformation uh, in alloys using ChemApp library. And for this talk, I would like to acknowledge my previous students, Nishant, Ashutosh, and Siddharth, and also Professor Inho Jung at SNU for encouraging the continuous development in this work, and also thankful. I'm also very thankful to the organizing committee at GTT for including me in this conference. Uh, so, in this slide, I would like to discuss how do we use ChemApp for solving phase transformation problems. So, basically, we are solving these four fundamental equations. So, the first equation refers to the interface velocity, which is in turn a function of the flux of a solute on the right side of the interface, for instance, as shown in the schematic phase B, for instance. So JK would be the flux in the phase B. JKLR would be the flux along the phase A. And then these two compositions are referred as the interface compositions. And now, in order to calculate the flux, we invoke uh, the uh, the equation which is shown here. So this is dependent on the interdiffusion coefficient of a solute, which is calculated through this formulation here, where we need the potential gradients, and we try to calculate the variation in composition with respect to time using the Fick's law, which is actually shown in this equation here. So we use ChemApp regularly to calculate the potential gradients so that we can determine the interdiffusivities, and also to calculate the interface velocity, where we need the interface compositions here. And so you following this methodology, we are calculating phase dissolution and phase growth problems, which I would be showing in this presentation. We are also solving solute redistribution, which is, in other words, doing homogenization calculation. We are doing precipitation and solidification calculations as well. So the first problem I would like to talk about is the ferrite to austenite growth in this steel composition, manganese carbon uh, composition, which is shown here. So this is very important. Ferrite to austenite growth problem is very important in dual phase steels, where the mechanical property of the steel is determined by the relative composition of the ferrite and austenite. And what you see in the phase diagram here is the nominal composition and the tie line, equilibrium tie line connecting the nominal composition here. Now, if you remember from the previous slide, we are trying to solve the interface velocity using the multiflux equation. So now in this case, we will have an interface velocity for manganese and an interface velocity for carbon, which obviously will be very different. So we need to accurately determine the flux, or most importantly the interface composition, so that we determine a unique interface growth velocity. right? Had it been a binary system, we can read the interface compositions during the growth process from the binary phase diagram. But since this is a ternary system, we have additional degree of freedom. So the uh, the system during the growth process can assume uh, any the system can assume uh, any number of tie lines across the planes, uh, and and uh, and we have to find out a unique a tie line, so that the interface velocities of manganese and carbon are almost equal or are within some uh, range of tolerance, right? So this is the exercise that we have to do for solving this problem. So we are going to consider the experimental data by speech. This is the initial microstructure, which is the combination of ferrite plus perlite phase. So I will go through the model formulation in a moment, but for the model setup, we assume that the transformation of perlite to austenite is instantaneous. So the volume fraction of them, so the initial volume fraction of the austenite is taken as volume fraction of perlite. Uh, Now, once we know the carbon content in austenite, which is assumed to be same as perlite, we can calculate the starting volume fraction of austenite. It's a one-dimensional model, so we have to convert the volume fraction into length scales, which comes out to be 0.744 micron, and the rest is, of course, occupied by ferrite phase. So, how do we start this problem? Is that we initialize the system, uh, get and do the first set of calculation uh, by doing a point calculation using ChemApp. We get the mass fractions of carbon and manganese in both FCC and BCC phase. We calculate the interface velocity because we know the flux, we know the interface compositions, and we check for this condition continuously. So there are two cases which can happen. The first case is that when the interface velocity of carbon is greater than manganese, which could be the case because at the starting growth process, the interface composition is of carbon is low, so the flux is higher. So the interface velocity of carbon is greater than manganese. So what we do is we increase the carbon composition, perform a point calculation again, recalculate the tie line here. Okay, and then we keep on doing this calculation till we achieve uh, the velocity of carbon roughly equal to the interface velocity of manganese. The other case could be when the interface velocity of manganese is greater than carbon, so we keep the carbon content constant and we increase the manganese content and repeat the process. And uh, uh, once we achieve the interface velocity difference between carbon and manganese within some tolerable range, we increment the ferrite length, and then we calculate the internal diffusion and continue this process. So once we implement this set of calculation, this is the final result that you see. So the experimental data that we see here is the data from Speech's work, and we have superimposed thermocalc simulation along with the calculation results from this work. And as you can see, at 780 degrees Celsius, we have captured the growth of austenite reasonably well compared to what is seen in the thermocalc simulation. So the particularly what is of interest is the growth pattern or during the initial stages. Uh, uh, as you can see in the thermocalc simulation, you can see there is this sudden increase in the in the austenite fraction, which is attributed to the interface control by carbon diffusion alone. But the data suggests otherwise, which means that during the initial stages, manganese diffusion is also important, which is actually captured in our model here, and then we consider both the carbon and manganese diffusion happening in the system till the system reaches the final equilibrium composition or final equilibrium austenite fraction. In their simulation, you see that the austenite fraction reaches a maximum value and then it starts to decrease again. So this is attributed to the redistribution of manganese in the austenite phase again. So, in our calculations, we did not have to assume a priori any para-equilibrium conditions, especially during the start of the growth, and the austenite growth came very naturally as an outcome of the model. So moving on, I would like to show one more case where we have connected the solidification calculations with the homogenization and dissolution calculation for a ternary alloy. What we did was uh, we performed we cast magnesium 16 and 1 weight percent aluminum alloy in a water cooled copper mold, and we inserted thermocouple across the thickness of the mold, and as you can see, with the varying thickness we could have as cast samples uh, with varying cooling rate. So in one experiment we could get as cast samples with different solidification features. uh, to give you an idea on the solidification model, we are considering the coarsening of the secondary arm spacing, and we are considering the back diffusion of the solutes in the HCP phase or in the primary phase, uh, which is responsible for the growth of the solid phase here. Then we assume local thermodynamic equilibrium condition, which is a valid assumption for the cooling rates that we are studying, and the solute balance, of course, and then all these four equations are coupled to solve for the growth of the solid phase here. And to show you the results, this is the as-cast microstructure variation with respect to cooling rate. We extracted the secondary arm spacing from the microstructure and the total second phase fraction, and we set up the model according to the conditions that we observed during the casting, and we calculated the secondary arm spacing variation with cooling rate and the total second phase fraction variation with cooling rate as well. So so the solidification model has been extended to multi-component aluminum alloys as well, and we are regularly testing it with different alloy systems as well. Now, once we have the as-cast microstructure, we need to dissolve the secondary phases. So now this system is very interesting because we have two different secondary phases, Mg2Sn and Mg17Al12, or the gamma phase, which are present in the microstructure. So we have to develop a calculation scheme through which we can consider the simultaneous dissolution of both the phases. So in this case, we start with the dissolution of Mg2Sn. We calculate how much tin is dissolved in the how much tin is dissolved. We redistribute that tin in the HCP phase, and in the second stage we dissolve Mg17Al12 and redistribute aluminum as well, and we continue this process for a given period of time. Uh, and once we implement the calculation scheme, the results are shown here. So what you see here in this panel is the total secondary phase fraction at 793 Kelvin with different annealing time. And as you can see, at 793 Kelvin, somewhere around 1 hour is sufficient to dissolve the phases. But at 743 Kelvin, of course, the dissolution kinetics are slow. And as you can see, the model and the experiments both follow a parabolic trend, which is expected in this case. Now, since we uh, uh, we consider the simultaneous dissolution of both the phases, so we can calculate the dissolution kinetics of Mg2Sn and Mg17Al12. So what you see here is that at 793 Kelvin, both Mg2Sn and Mg17Al12 dissolve very quickly within an hour. But at 743 Kelvin, the dissolution kinetics of Mg2Sn are slower, so the overall dissolution kinetics of this alloy is governed by Mg2Sn phase. So this is an information that is directly coming from the model. Now moving on, I would also like to show how we are using the homogenization calculations to predict the homogenization parameters for nickel alloy processing. So typically, a nickel alloy after casting and double war, the homogenization is performed in this given temperature range, followed by extrusion, solution treatment, and aging. Now, homogenization is very important step because we want to redistribute the solutes back in the gamma phase in the nickel matrix, and we also want to dissolve all the secondary phases so that we do not face any problems during the extrusion stage. So it's very important stage in order to control the downstream processes of downstream processing of nickel alloy. So how do we start? We start with the as cast, the microstructure after the war process. So what we did was we implemented a sorting algorithm in order to get the microsegregation profile of the solutes. So what we do is we divide the as cast microstructure into different into grids. So for instance, you see a grid of 300 micron by 300 micron, and we perform EDS analysis at every 5 micron. So we get somewhere around 9,000 points, and then we implement a sorting scheme in order to calculate the segregation profiles. And these segregation profiles are actually input to the homogenization calculations. So once we perform the calculations, and we can compare it with the experimental data, because we repeat the same sorting algorithm after the homogenization stage as well. So what you see here is the comparison between the model and the experiment. So delta here refers to the maximum, the difference between the maximum and minimum solute concentration after a given homogenization time, right? So delta being highest is of course the ASCA stage, and the ideal homogenization would be when delta is 0, right? So, and of course, with increase in homogenization time, the delta is decreasing, right? And this is and then we have to find out the correct homogenization time, so that we have delta within some acceptable range. And as you can see, we performed this type of calculations and comparison with the experimental data for chromium, iron, moly, titanium. I've shown the results for chromium and iron, and you can see that the model and the experiments are reasonably good. The comparison is reasonably good, but when you see the thermocalc calculation, the thermocalc is overly predicting the delta. So in the thermocalc calculations, the homogenization kinetics are faster for this particular nickel 925 alloy. So in the end, I would like to mention that we are constantly using these calculations for optimizing the dissolution time, the homogenization time for different alloys. And in the next stage, we are also working on the strength prediction of these alloys. So we have also developed a precipitation model which can predict the number density and size with respect to aging time. And we are using the output from the precipitation model as an input to this strength based modeling framework that we are using now. So what you see here in this graphs is the strength variation for different binary magnesium alloys. And so we have tested different solutes, for instance, zinc, aluminum, tin, at different concentrations. So you see the variation in concentration of zinc, and the variation between zinc and aluminum is also there, and there is a variation of aging temperature as well. So what we have done in this framework is that we uh, are not using in any calibration parameters depending on the solute or the concentration of the solute. So this is a unified framework where we are using one set of model parameters to predict the strength for this for different magnesium alloys. And we are regularly now testing this for other alloy systems as well. So the details of this strength calculation framework can be found in this publication. So thank you very much for your kind attention, and I can take any questions if you have. Thank you very much.